Hi.
Hello.
Hello.
Hi,
Professor.
I post the office. I post some tutoring hours from a former student who taught my class last semester. So he has some tutoring hours through using Zoom. I post it as an announcement in campus, so you can take a look if you need help. His time slot, one of the time slot actually overlap with the lecture, but the other two, Tuesday and Thursday, will work for you guys. In case you need help. We are doing section 6.3. Last time we talked about you have a vector, you project this onto a line. You project it onto a line here. This is the projection. Okay. So now we want to generalize this. Okay. We want to generalize this. Okay. So this is a generalization of what we did earlier, last time. In this case, you have W, which is a plane. Okay. And you have Y. You have Y. You want to project this onto the plane. So you drop a perpendicular onto the plane. So this guy here is the projection of y onto W. Okay? And this works for higher dimensions also, okay? Not just into a plane. In general, we are talking about W as a subspace. I'll talk about the general case a little bit more, okay? But let's go through this example first, okay? So the technique we are going to use depends on the fact that this one is an orthogonal basis. Do you know what this means? Orthogonal? It means these two guys are perpendicular to each other. How do we check it?
Dot product is equal to 0?
Yeah, dot product is equal to 0. Very good. So we want to check U1 dot U2 is indeed equal to 0. 5 minus 4 minus 1. Okay? 5 minus. Okay, so you actually end with 0. So now, in order to do this problem, this is what we do. Okay? So we want to write, this is what we do. We want to write y equal to C1 U1 plus C2 U2 another vector. Okay? And then you try to determine and then determine C1, C2. Okay. This vector Z is in W curve. Okay, that means in the picture there, this guy is going to be Z. This guy is going to be Z. That's my Y. Okay, this is the projection. Okay, and then this is C is in W curve. So this guy here, eventually, this one is the projection. Okay, and then we just need to determine C1 and C2. Now, the way we determine C1 and C2 depends on the fact that U1 dot U2 is equal to 0. So what we do is that this is what we do. We have done this many times last time. We take this guy and dot U1 on both sides. Okay. Then we have C1 times U1 dot U1 plus, now here you have a U1 dot U2. Now both of these are going to be 0. This guy is going to be 0 because those two are perpendicular to each other. So this one is equal to 0. This other one is also equal to 0 because Z is in W curve. Okay? C is in W curve, that means it's perpendicular to every vector on in this subspace W. In particular, it's going to be perpendicular to U1 because the U1 and U2 are in W. Okay, so if I want to draw this more specifically, there's some vector U1 here, and some vector maybe something like this, which is U2. In this case, they are actually perpendicular. Maybe I should draw it so that they are perpendicular. Okay, U1, U2 are perpendicular. Okay, so what is C1? C1 is going to be y dot U1 divided by U1 squared. And then you can do the same thing for C2. What is this? Y dot U1, Y is what? Y is 1, 2, 3. 1, 2, 3 dot U1. What's U1? 2, 5 minus 1 over, oh my God, I'm running out of space. Okay. U1 squared. U1 is this guy. 2 squared plus 5 squared plus 1 squared. Square root. No square root, just the whole thing squared. Okay. So that is my C1. Okay. Which is equal to 10 plus 2, 12, 9 over 30. 3 over 10. Is that correct? Okay, 3 over 10. Do you guys follow this? Are we okay?
Yeah.
Okay, good. Okay, very good. C2, what is C2? C2 is going to be y dot U2 over U2 squared. Y dot U2 is 1, 2, 3 dot U2 minus 2, 1, 1. 2 squared plus 1 squared plus 1 squared, which is equal to 2 plus 3 is 5. 5 minus 2 is 3. 3 over 6, which is 1/2. So the projection of y onto W is going to be this guy, 3 over 10 times U1 plus 1/2 times U2. Okay. Whatever that is, turn out to be minus 2 over 5, 2. Okay.
What about Z?
Huh?
What about Z?
C is, I mean, that is not part of the projection. It's the leftover. C is from here to here. This other vector.
Oh, okay.
C is the one. C is in W curve. Okay.
Okay, thanks.
So if you want to find the distance of this point to this plane, the length of this Z will be the distance. Is it okay?
Yeah. Sorry, I got confused.
No, that's fine. I mean, it's really reasonable to ask. So the projection is this guy. Okay. Z is actually equal to. Okay, so how do you? Okay, so your question is how to find Z. If I need to find Z, Z will be equal to my original, which is Z is equal to y minus y hat, basically. Y minus the projection. Y minus the projection. Okay, which is 1, 2, 3 minus that guy. Which is equal to which is equal to 1. Let me do my arithmetic. 5/7, 0, 14/5. Okay, so this vector, you see, are you guys with me?
Isn't it 7/5?
7/5. Thank you. I messed up. Terrible. Now you can check. You can actually check. If you want to check, you can check that z dot u1 should be equal to 0. Because z is perpendicular to u1 and also u2. Can you see that z dot u1 is 0? Can you check mentally? These two dot each other. 7 and 2 get 14. 14. It's okay? Do you guys check mentally? How about c dot u2? It's also supposed to be 0. This guy dot this guy. It is 0. It's okay? So now you have actually 3 vectors. All orthogonal to each other. It's the u1, u2, and z. Any question about this example? It's pretty elaborate, this example. I mean, it's a conceptual thing. You need to understand this picture when this guy projects onto the plane. It gets generalized to higher dimension, of course. Okay? It got generalized. Okay, so we are going to write down the generalization now. Okay? Okay. We are just generalizing what we just did to a higher dimension. W a subspace of Rn. And this one is called projection of y onto W. Okay? And then if And the projection, this is the projection, okay? This guy is the projection. This is the formula for the projection, how to obtain the projection. We just did that actually. Hopefully you understand what we are saying here. There's a picture. This is really summarizing what we have done, okay, generalizing it. I mean, nothing more than that. So you have this guy. It doesn't have to be two-dimensional, but there's no other way to draw it. Okay, so this is my W. Okay, and then you have your Y here. Okay, you project it down here. You project this down here. You get your Y hat, which is equal to the projection of Y onto W. Okay, and then you get this guy Z in W per. Anything else? Yeah. That is the picture. It's just essentially the same picture. Any question? It's just generalizing what we just did. How are we doing? Now this guy here, Z, okay, let me write it down here. Any questions so far before I talk about some more properties? So Y hat, it is a projection, is the closest point in W to Y. That means among all these different points, this point is the closest to this point, those 2 points here. Okay, this is closest. So this point is the closest to this entire plane. Okay, this entire plane here. This green dot, okay, the closest point on this plane to the green dot is this point here. Maybe I use this color. Okay. So the distance of Y to W is defined as the distance of Y, this point to the plane, is defined as the distance between Y and Y hat and the projection. Okay. You guys know what this is trying to say? So in the earlier example, we just did, we got, what did we get? We get z is equal to, in earlier example, we got z is equal to 7/5, 0, 14/5. Okay, so the distance of y to w is the magnitude of this guy. Okay, it's the distance between those 2 points, which is the distance between these two is this vector. Okay, so it's going to be just equal to square root of 7/5 squared plus 14/5 squared. Whatever this is. Is it okay? Any question? We can do another example. Okay. So basically, what this is saying is that here you have the projection. Okay. So this z is in the W perp, is perpendicular to the entire subspace. Okay. And the length of this vector is considered the distance from this vector to the subspace. It's actually the closest, okay? It's the distance from this to the closest point in the subspace. Do you guys get what we are trying to say there?
Yes.
Okay, good. I'm going to do one more example on this, okay? We'll do one more example. Let's say U1. Is this the same example as I did earlier? It's a little bit different, right? No, it's slightly different, which is good. Okay. Okay. So what would be the closest point? From Y to W span. Okay. Distance. Okay. First thing we have to check. First thing we have to check is that these two guys are actually perpendicular to each other. Are those two perpendicular to each other? Are they perpendicular to each other?
U1 and U2.
Yeah, U1 and U2, are they perpendicular to each other? Oh, is that the same example I did earlier? Oh, I have to. Let me do another different example. This turned out to be exactly the same example I did earlier. So I'm going to change these numbers. I'm going to change these numbers here. Okay. 6. Okay, better. Okay. Okay. It turned out to be the same example earlier. Okay, so this is better now. So are these two perpendicular to each other? Because the technique we use depends on these two perpendicular to each other.
Yes.
So check U1 dot U2 is indeed equal to 0. Okay? So now the closest point from Y to W, okay, is the projection. So part A, we need to find the projection of Y onto W. Okay? And let's call this Y hat. Okay? So this guy, so Y, we can directly use the formula. Okay? So this guy will be Y dot U1 over U1 square, okay, times U1 Y 2 over U2 square U2. And that's the projection. The projection, that is the closest point, okay? That is the closest point. W. Okay, and you just need to plug it in and then compute it. Why don't we plug it in? Y dot this guy dot 3 minus 1, 2 divided by 9, 10, 40. Is that right? Let me know if I make a mistake, okay? I'm just keep going. Times 3 minus 1, 2 plus minus 1, 2, 6 dot the other one 6 times 1, 2, and this one will be equal to, okay, help. 12 minus 5 is 7. 7 over square root 14. 3 minus 1, 2 plus, what is this? Minus 1 minus 2 minus 50. Did I do it correctly, guys? Did I do it correctly?
Shouldn't the first one be a 9 over root 14?
Where?
Or
This is 9. It's not 7.
hold up, I'm probably wrong.
Yeah. It's 12 minus 7. 12 minus 5. I think it's 7. Oh, there's no square root. That's why. Okay, sorry. There's no square root. That's the problem. Because it's not the norm, it's the norm square. Okay, it's better. I'll just wait until you guys convince, because I also make mistake. I don't have the answer here. It's just plugging into the formula. Hopefully you understand where that formula come from. Okay, because we did the earlier example showing the steps. Is it okay? I don't have the answer with me because this I don't have it with my notes. I have the problem but not the answer. But it seems okay. Everything seems okay. These two are orthogonal to each other. We check that. Okay, and everything is just coming out from the formula.
Yeah.
It's a little bit ugly. Okay. Oh, 7/14, which is good. 1/2. Is it 1/2? 7/14 is just 1/2. And this one is what? 5/2. Oh, this is not bad. It's a lot better than I thought. I was concerned with the square root, how to combine it. Okay, so now what do we get? We have 3/2 minus 5/2, -1. Is that correct? -1/2, -1/2, 5/2. This one is 2. And then I have 1 plus 5. Which is do I do it right? Do I do it right?
I think the last one should be -4.
The last one is -4.
Yeah.
2, 2, 4. This is 1. This is 1. And this is 1 plus 5, right?
Yeah, it's -5. Wait, it's positive?
1 plus 5 is 6.
Oh, sorry, my bad. My bad.
Is it okay? Is it okay? So what this is saying is that is the following, okay? So it turned out for this particular problem, this guy is already the projection. It actually lies on the plane. Do you guys know what I'm talking about? Yes or no? Do you notice that this one is already my y?
Yeah.
So in this case, yes?
Yes.
Okay. So it turns out that this guy is 1/2 of this minus 5/3 of the other one. Okay. That means originally my y is already like this. So you have this u1 and u2. Okay. My y is already lying here. So the projection will be itself in this particular case, okay? So the closest point will be y hat, which is this answer here, okay? Which is this answer, which turned out to be itself. So what will be C then in this case? What will be C? C will be the difference between the two.
The 0 vector.
Will be the 0 vector. So what will be the distance? Find the distance from y to w. Distance from y to w would be equal to what?
0.
Will be equal to 0. Okay. So that's good. It's a little bit degenerate, okay, that particular problem. I can do another one which is not degenerate then, okay? So we'll do one more then, okay? We'll do one more. Okay? Five minus 2, 1, 1, 2, minus 1, minus 1, minus 1, 10. Okay, so we'll do this one. And I think this one is not degenerate, so it will be better. Okay. So everything remains the same. Okay, can we check whether u1 dot u2 is 0? Hopefully it is. u1 dot u2, is it 0? 5 minus 4 minus 1. So here, u1 dot u2 is equal to 0. Okay? So in this particular example now, what we have is going to be, I'm going to write it here. Okay? So this one will be equal to y, which is this guy, dot 5 minus 2, 1, divided by 5 squared plus 2 squared plus 1 squared. Okay? And this one will be 5 minus 2, 1 plus minus 5, 10 dot 1, 2 minus 1 divided by 1 square plus 2 square plus 1 square. 1, 2 minus 1. Same structure, okay? So what are these numbers now? Okay, you guys help me out. 10 plus 10 is 20. So this one will be 15. Is that correct? $15 divided by 30. Fantastic. This is a negative. Negative 10, negative 10, negative 31. Is that right? Negative 10, negative 21. Divided by 6. Okay. 1/2 5 minus 2, 1 plus minus that, okay? Minus 7 over 2, 1, 2 minus 1. I will write this out to make sure I don't make any mistake there. 5 over 2, negative 1, 1/2, subtract 7 over 2, 7, minus 7 over 2. Okay. What do I get? The first one is going to be negative 1. The second one is negative 8. The third one is it correct? I think it's correct. So that is the projection. So now the picture looks like this. Now you have here, you have my y, you do the projection onto here, and this guy is the projection. The projection is -1. This is the projection. Okay, this vector here. This vector here. Is my -1 minus 5 is equal to -1 minus 5 and 10. So what will be my vector z? What will be my vector z? Okay, so part A, so this is the answer for part A. Okay, so part B, find the distance of y to w. You need to, this is for part B, you need to get z. How do I get z? How do I get z? This vector. Anybody? What is this vector z?
Y minus the projection.
Y minus the projection, so this one it will be -1 minus 5, 10, subtract -1 minus 8, 4, and then you will get 0, 3, and 6. Is that right? So what's the distance? Part B, find the distance. Distance of y to w is going to be the square root of this guy's 0 squared plus 3 squared plus 6 squared, square root of 45. Okay. Any questions so far? We finished that section. We're going to do the next section. Any question? Or is something is buried? The screen is really buried. Is it okay? Sometimes it happens. It has happened before. Maybe we have to just wait a little bit. Tell me whether it make any difference. I think it's sometimes it's a bandwidth issue. We'll just wait. I mean, it usually corrects itself. I can also leave and come back in and see whether it helps. How long has it been going on? How long has it been going on?
Maybe 5 minutes.
5 minutes. Oh, that's bad. You guys will let me know earlier when it's happened. How much did you miss? Everything?
We could hear you. It's just the board is hard to see. Yeah.
Oh, this one we still have the whole thing here, so I'm not erasing it.
Yeah.
So is it better now or not? No? I'm going to leave the meeting and come back in and see whether it helps, okay? I'm going to leave and then come back in. Is it better, Key? Okay.
Oh yeah, that's better.
Is it better? Yeah, it's just sometimes it's a little bit slow. It happened before with other classes. Usually it's in the afternoon though. In the morning it's better. Okay, so if this happened for the last 5 minutes, you probably didn't miss too much. I mean, everything is still on the board. The earlier example was a little bit too degenerate anyway. The end of the projection is equal to itself. Okay, so this one is a little bit more interesting. So we want to project this guy onto the subspace. okay, onto the subspace spanned by these two vectors. In order for this methodology to work, you need to make sure that these two guys are originally perpendicular to each other. Okay, these are all perpendicular to each other. So, and then you just use this formula. Where this formula come from, I explained it to you at the beginning of the lecture through an example. Okay, so you just plug in the formula, and then you get the projection, and the projection is -1 -84 after all this arithmetic stuff. Then this is the closest point from Y to the plane W, to the subspace W, Okay, and the difference between the two is this vector Z. Z is in W perp. Okay, this Z here. Z is in W perp, is perpendicular, and the distance of this will be the distance of the point to the subspace. In this case, the plane. Okay. How are we doing? I'm going to go to the next section. Is this still okay? The resolution?
At least for me, it just dropped again.
Yeah, it's blurry again.
It dropped again. It's blurry again. All right. It always happens at this time of the day. I don't have this problem in the morning. It doesn't look like I have this problem in the morning. Is it still bad?
Yeah.
Okay. Okay. I don't know really what to do. I will leave again and come back in. Okay? And see whether it helps.
Something in the chat.
Huh?
He said something.
Don't use the chat. Is that what you're saying?
No, Luca recommended bringing the Wi-Fi router closer to your computer.
Wi-Fi router closer to the computer. It's in another room.
Or is anyone on Netflix? I remember that happened before.
Yeah, let me try. Okay, hold on. I don't know. I mean the whiteboard is not movable. It's on the wall.
But
That's
now
one.
the quality's okay. It's it was better for like a second, and now it's back to being bad. It's better. It's okay now.
So going back out and come back in seems to help for a little while. Okay. I am going to try to do 6.4 and see how long it lasts. Okay? Okay. So you remember the earlier examples we did depends on those U1 and U2 being perpendicular. Okay. So what happens if they are not? Okay. What happens if they are not perpendicular? So we can try to make them perpendicular. Okay. We try to make them perpendicular. So in general, okay, in general, we want a process, okay? We want a process to make things perpendicular. So making things perpendicular is not that difficult if you only have two vectors. Okay, let's say W2 is span. Okay, this is the setting. Okay, I'm going to use the general setting. Okay, so you have W1 is spanned by U1. Okay, so W2 is spanned by U1 and U2. Okay, what does this mean? You have U1 here, okay, and let's say you have some U2. Let me make it shorter. Now U1 is going to be this guy. It's going to be this line. U1 is this line W1, and then you have W2. W2 is on this plane now. Okay, W2 is this plane. It's spanned by U1 and another one which is called, let's say, U2. Let's say this one is U2. Okay. Now these two U1 and U2 are not perpendicular. U1 and U2 are not perpendicular. And we want to recreate another vector. Okay. We want to find V1, V2, so that V1, V2 are orthogonal. Okay, and the span of U1, V2 is the same as the span of U1, U2. Okay, you guys know what I'm talking about? So W2 is a plane, W1 is a line. Okay, and you have two vectors here. W1 is spanned by U1. W2 is spanned by U1 and U2. But U1 and U2 are not orthogonal. Okay, I want to get two vectors. Okay, in W2 which are orthogonal. So they span the same thing. Both of these span W2. Both of these are equal to W2. This is the same. This is W2, and this is W2. Do you understand what we are trying to do here?
Yeah.
Okay. So all I need to do is the following. Conceptually, it's pretty simple. Conceptually, okay, we'll set V1 equal to U1. The first one doesn't really matter. Just keep this one as U1 and V1 the same. The second one, okay, so what should be V2? V2 is just use this one as V2, the one we just keep talking about earlier. We talk about projecting this guy onto U1, which is this guy here, doing this projection here. Okay, so this one is perpendicular now, and then this vector here, this vector here, the C that we talked about earlier, this guy here, should be our V2. Okay, so our V2 will actually be the difference between the original one, which is U2, subtract the projection of U2 onto W1. Do you guys understand what is going on? The projection of V2 onto the line. Okay, you do the subtraction, then you get that perpendicular vector. Okay, and now this V1 and V2 will have this property. This V1 and V2 still span W2. Okay, it still span W2, but they are now perpendicular. I will do examples on this, but I want to make sure that you understand this first.
That's good.
Is it okay?
Yeah.
I'm going to generalize this. Okay, I'm going to generalize this. Okay, so now it's going to look like this. Okay, this is generalizing now. Okay. This is a generalization of what we talked about earlier. Now you have this guy is a basis for this, for W. That means these guys, what does that mean being a basis? Basis need to span it. Also means that these guys are linearly independent. Okay? They are linearly independent, but not necessarily orthogonal. Okay? Find an orthogonal basis for W. Okay? Now these guys are not orthogonal, but I want to find an orthogonal basis for W. Okay? So the procedure is the following. I'm not going to have enough time to do an example today, but we'll do it on Wednesday. Let me write down the algorithm for you. Okay? So V1 is equal to U1. That's step number 1. Okay? So span and W1 is just equal to the span of U1, which is the same as the span of V1. Okay? So this is just picking the first vector. Doesn't change. U1 and V1 are the same. Okay, nothing happening. Now, the next thing is that V2 is going to be equal to the vector U2, okay, minus the projection of U2 onto W1. This is what we did earlier. You're projecting this guy, subtract the projection onto that line. Okay. So now we have W2, which is the same as span of U1, U2, which is the same as the span of V1, V2. And V1 and V2 are now orthogonal. Okay. V1, just like what we did, this is essentially what we did earlier in the earlier example. But this can be extended. So now we have V3. V3, you're going to take U3, and then you're projecting this onto W2, which is the plane. Okay. Take that U3, project it onto W2, take the difference, then you get the one perpendicular to it. This difference is the one in the curve, right? So W3 now is the span of U1, U2, U3, which is the same as the span of V1, V2, V3. And then you keep doing this until the end. Until the end, you will basically have P vectors. VP, sorry, UP minus projection of W P minus 1 of UP. Okay. So at this point, okay, WP will be equal to the span of U1, U2 to UP, which is the same as the span of V1, V2 up to VP. And now the WP is in fact the same as W now, okay, because it's spanning all this, using up all the P vectors, okay. And then on the other side, these guys are all orthogonal. So we are going to use this algorithm. Next time, this is called the Gram-Schmidt orthogonalization process. Okay, we're going to use this algorithm to make our orthogonal basis. Okay. Is the quality of the projection okay, or has it deteriorated again?
It's good.
Okay. I just want to get an idea. I mean, how bad what kind of problem I have. We have to last another 3 weeks. I think it's sometimes a little bit intermittent, but it's not too bad. Do you guys understand conceptually what this is doing? It's an iterative process. It's an iterative process. You just keep doing. Maybe I can draw a picture. Okay, I'm going to draw a picture. I have a little bit of time to draw one picture. Okay. Okay, so I'm going to draw a picture. Draw a picture here. So you start out with, you have this guy called U1. You have another one called U2. Okay. And you have another one up here called U3. Okay. And they are not perpendicular. So what we are doing is that this one is my, the same one. This one will be V1. Okay. And then you drop a perpendicular of here to here. So you end up with this guy here. So these two are perpendicular now. This one is V2. Now this V2, that guy, this V2 is the same as this one. Okay. This one is also V2. Okay. So it's this guy to here, but these two are parallel. This one and this one are parallel. So the third one is going to drop a perpendicular of this guy onto here, and then you end up with something over here, which is V3. Okay? And now V1, V2, V3 are all perpendicular. Okay? So this next one, this other one is this orthogonal. Okay, we use blue. Let's do one here. This one is V3. Okay? And this one is another perpendicular. Hopefully you understand what's going on. That's essentially what's going on. You just put in, do it one at a time. Are we okay? I just need to do some actual example next time for this section. And then I can move on to the next section. So this section is, the whole section is about this process. So it's important to be able to do that. It gives you a way to get an orthogonal basis. And I talked about the importance of having an orthogonal basis last time. Because if you get an orthogonal basis, you scale it, it become orthonormal basis, then you have a matrix. That matrix as a transformation will preserve the inner product, which means that it preserves the length and preserves the angle. And that's important. So we'll use that a little bit in chapter 7. Okay, any question? Are we okay?
It's going to be a fun homework assignment.
Huh?
It's going to be a fun homework assignment.
This is terrible.
No, I'm being sarcastic.
Well, this is terrible in terms of actually computing it.
Yeah.
So much like computation, just like numbers adding and subtracting.
Yeah. But there's a couple of tricks that you can use. Maybe I found out the trick. So when you do this, guys, if you end up with a lot of fractions, you can scale it. These guys, I mean, the first one you don't have. I mean, even the first one you can scale it. You can scale this. You can scale the VI's to get rid of fractions. Okay? Because when you scale a vector, it's still orthogonal. So if you do that, then you don't have to deal with as many fractions. Okay?
Thank you for that tip.
So we'll actually see it next time when we actually work through the example. Yeah, these things are really long and terrible. But we need to understand this exists and we need to do some examples. Okay? So that we know what's going on. Okay, anything else? You guys are learning a lot. Okay. See you guys on Wednesday. Okay?
Bye, Professor. Thank you.
Okay.
Thank you.
Okay.
Thank you.
Bye. Bye.